Hello everyone and welcome to Control Engineering tutorials. In these tutorials we present real and applicable knowledge of control engineering, control theory, dynamical systems, automation and robotics. In this video we explain one very important topic that's often not being properly explained or even worse, completely neglected in classical control engineering classes. After watching this video tutorial, you will learn that zeros of transfer functions can have a dramatic effect on the transient response of a dynamical system. For example, over here you can see a prototype of a transfer function. Zeros are simply zeros of the numerator. If this zero is close to the poles of the transfer function, then the overshoot of the transient response that you can see over here will be dramatically increased. Then you will also learn that zeros that are in the right half of the complex plane can have a devastating effect on the transient response. Consider this transfer function over here. The zero is obviously in the right half of the complex plane. This is the response of such a system. You can obviously see that instead of going upwards, that is, instead of going like this, the transient response goes downwards. And this is a direct consequence of the fact that the zero of this system is in the right half of the complex plane. Such zeros are called non-minimum phase zeros. The importance of this phenomenon lies in the fact that such a response can completely destroy your physical system, and control system design for systems with non-minimum phase zeros is very challenging. Before I start with the explanations, I would like to mention a few things. First of all, those of you who are my subscribers or who follow this channel know by now that I always create a post that nicely summarizes everything that I will explain in this video, and consequently here is the post. This post contains equations, MATLAB codes, and figures. A link to this post is given in the description below. Secondly, it took me a significant amount of time, energy, and planning to create this video and this post, and consequently I kindly ask you to press the like and subscribe buttons. Thank you very much. The first important thing that you will learn in this video is that zeros close to the real poles attenuate the effect of the poles on the system response. And this is a very important observation. So let us consider this transfer function. And let us compute an impulse response of such a transfer function. An impulse response is simply an inverse Laplace transform of this transfer function. To compute the inverse Laplace transform, we obviously need to use the partial fraction expansion. That is, we need to expand the transfer function in this form, where C1 and C2 are coefficients, and the terms in the denominators, that is the term s plus 1 and s plus 4, corresponds to the pole. We basically compute the coefficients C1 and C2 by using the cover method. C1 is simply W1 times s plus 1 evaluated at s is equal to minus 1, and we obtain 4 over 3. Similarly, C2 is minus 4 over 3. Substituting these two values, we obtain the equation number 4. Now, obviously, if we apply an inverse Laplace transform to the equation number 4, we obtain equation number 5. And this is the impulse response of our original system. Next, let us add a 0 to our original transfer function that's shown over here, and let us scale this transfer function. Here is the 0 term. It is s plus 0.9, and 0 is obviously at minus 0.9, and this 0 is deliberately chosen such that it's close to this pole over here, that is close to s is equal to minus 1. So to summarize, we modified our original transfer function shown over here by adding a 0 at minus 0.9 that's close to the pole at s is equal to minus 1, and by introducing this scaling constant. This scaling constant is introduced in order to make sure that the transfer functions w1 and w2 have the same dck. Now, let us compute an inverse impulse response of w2 transfer function. To compute the inverse impulse response, we obviously need to compute the partial fraction expansion, and here's the partial fraction expansion. Now, what is the effect of adding a 0 at minus 0.9 that's very close to the pole at s is equal to minus 1? Well, the effect is that this term over here, multiplying 1 over s plus 1, is significantly decreased. And moreover, its sign is being changed. Also, the other term, the other constant, multiplying 1 over s plus 4, is increased and the sign is being changed. Now, we can immediately see that the 0 at s is equal to minus 0.9 close to the pole significantly diminishes the value of the coefficients c1. This comes from the fact that in order to compute the partial fraction expansion by using the cover method, we use this formula. This formula is evaluated at s is equal to minus 1. Now, since the transfer function has a 0 at minus 0.9, this whole term is going to be very small. That is, a 0 close to a pole decreases the effect of that pole on the response of the system. The impulse response of W2 system is given like this, and this is a very interesting impulse response that we will discuss in the sequel. Here's the MATLAB code that I used in order to generate the impulse response and the graph that you will see in figure 1. That is this graph over here. This graph shows the impulse response, W1, this is the function without zeros, and W2 is the impulse response of the system with a 0. And we can obviously see that the system with a 0 has such an impulse response. Initially, we have a large value of impulse response, and the impulse response slowly dies out. On the other hand, if we don't have a 0, what happens? We start from 0, and then we have an overshoot, and then the impulse response goes down. And this is a big difference, as you can see by observing this impulse response of the function without the 0 and this impulse response of the function with the 0. The 0 basically acts as a derivative action, and I will explain this very important phenomena in the sequel. Next, you will learn that zeros tend to increase the overshoot of the system. Consider a prototype transfer function given by the equation number 10. Here, omega n is a natural undamped frequency and zeta is the damping ratio. Graphically, the poles of the system are given over here. That is, this graph shows the poles of a prototype system. The poles are given over here, and here's the graphical interpretation of the poles. Omega n is simply a distance from the pole to the origin, and zeta is a cosinus of angle between this vector connecting 0 and pole and the real axis. So zeta is cosinus theta, and omega n is simply a distance. And you can see over here real and imaginary parts of the poles that are shown over here. Next, let us transform our prototype transfer function in a more suitable form. We can simply take this constant and put it over here. And as the result, we obtain this form over here. Next, let us add a zero term to the prototype system. Here's the term that we will basically add, or better to say, we will multiply our original transfer function by this term over here. The zero is located at minus k zeta omega n. Let us represent this zero graphically. This is a complex plane. The poles of the systems are given over here. This distance over here, measured in absolute value, is zeta omega n. And if, for example, k is equal to 2, we place a 0 over here, since this distance is 2 times zeta omega n. That is, by varying this parameter k, we can investigate how zeros influence the dynamical response of the system. We are interested in several scenarios. What happens when this zero over here is close to the real part of the poles? What happens when this zero is relatively far away from the real parts of the pole? The final form of the transfer function is given over here. Let us now investigate the influence of the parameter k on the transient response of the system. This graph shows this influence. Next to this graph, I will draw another graph that represents the complex plane. The poles are obviously given over here. And this distance is basically a real part of the poles, and this distance is zeta omega n with a minus sign. Let us see what happens when k is going to infinity. This corresponds to the transient response of the system without the zero. The blue line in this graph shows the response of the system without a zero. We can see a damped oscillatory response. Next, let us set k is equal to 5. Graphically, this means that we locate R0 over here. 2, 3, 4, 5. So 0 is located over here. Remember that zeros are given. S is equal to minus k zeta omega n. And the magenta line represents the response. We can obviously see that overshoot of the system, that is, this value over here, is increased compared to the system that doesn't have a zero. Moreover, the response is faster. That is, the rise time decreased. Next, let us see what happens when k is equal to 2. When k is equal to 2, the 0 is located over here. And the black line is the response of such a system. We can see that overshoot additionally increased. And moreover, the rise time decreased, that is, the system responds faster. And finally, let us see the worst case scenario. What happens when 0 is equal to the real part of our poles? And you can see clearly a devastating effect. You can see that the overshoot is above 100%, so your system explodes. By considering this simple example, we learn one very important fact. Zeros increase the overshoot. At the same time, they make the response to be faster, however, more unstable. Here's the MATLAB code I used to generate this nice figure. It's given over here. I'm basically using the standard commands such as transfer function, plotting step, etc. Now, let us make the following substitution in our original system. We will define a new complex variable v is equal s over omega n, and we can substitute this variable in our transfer function, and we can decompose the equation number 17 to obtain the equation number 18. The equation number 18 has two parts. The first part corresponds to the system without zero, and the second part basically comes from adding a zero to the system. And we can distinguish two transfer functions, wf1 and wf2. Let the inverse Laplace transform of wf1 be denoted f of tau. That is, in the complex domain we have f1, and in the time domain we have f of tau. Basically, this is an impulse response. F of tau is an impulse response. Then, it's a very well-known fact that the Laplace transform of the first derivative, that is, of f dot of tau in the tau domain, is basically in the complex domain v times vf1. Notice here that v now plays the role of s since we made the substitution. This implies that this whole term, that is the term given over here, I will use different color to denote this term, or better to say this term over here, is the first derivative of the function f of t. Consequently, this term can be interpreted as the first derivative that is scaled by a constant 1 over k zeta. So this is the effect of the zero. The zeros actually add a derivative term to our transient response. And this explains the fact that we have a significant overshoot. Because initially, when the response starts to increase, the derivative is significant. And this adds additional value to our transient response. And you can clearly see this phenomenon over here. The red line is the system without a zero. The dark line or the black line is the response of the second term corresponding to derivative action. And we can see that initially it's very high, and then it decreases, it also oscillates. And finally, the blue line is the response of our function that's basically equal wf1 plus 1 over k zeta wf2. And this is our original transfer function. So this term over here gives this part of the response, and this term over here gives this part of the response, such that when we sum everything together, that is, when we superimpose, we obtain the blue line. And this is the reason for the overshoot. The derivative action that's in the zero creates the overshoot, and we can see that as k decreases the value, this term over here starts to increase. And finally, we will explain non-minimum phase zeros and their effect on the transient response. So far, we consider zeros in the left half of the complex plane. However, the zeros can also be in the right half of the complex plane. That is, they can be over here, they can be over here. These zeros are devastating. They create significant problems. They can destroy your physical system, they can create damage, and they can be very challenging for designing a control system. So we will modify our prototype system to look like this. Here we introduce a zero, however the zero is now located at the right half of the complex plane. It's equal to k zeta omega n. The analysis is equivalent to the analysis I performed in the previous segment of this video. That is, I will simply decompose my transfer function like this. I explain the origin of this term. However, notice over here that we have a minus sign. We have a minus sign. And let us see what this minus sign will do in practice. So once we simulate the step response, we will obtain this graph over here. The red line is the response of the system without the zero. We can see a nice damped response of the system. The black line is a response due to the zero. That is, this is a derivative action. And we see that initially this whole term is negative. This is because we have this constant in front of the second part of the transfer function. And once we add black line and red line together, we obtain the blue line, and the blue line is the final response. We can obviously see that initially our system goes in the opposite direction, and this can be devastated. This can completely destroy your system. This can kill someone, can create damage, etc. Also, you need to design a control system that will minimize this effect, and this is quite challenging. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.